At the center of a dead star, matter has been pressed beyond every familiar form. The spaces inside atoms are gone. Electrons and protons have been driven together, leaving behind a sphere no wider than a city, yet heavier than the sun. Beneath its thin, burning surface, each layer becomes stranger, until even modern physics begins to lose its certainty. Before we move closer, take a moment to settle into the room around you. If quiet journeys through deep space help you relax, sleep, or simply think more slowly, you can support the channel with a like, a subscription, or by sharing this story with someone who may enjoy it too. You can also leave a comment with where you are listening from and what time it is there. It is always comforting to imagine these distant worlds being heard from many different places beneath the same night sky. Lower the lights, if they are still bright. Let a fan turn softly in the background, or allow the room to remain completely still. Find a position that feels easy to hold. Loosen the muscles around the shoulders and jaw, and let the weight of the day begin to rest somewhere else. The object waiting ahead does not shine like an ordinary star. Its light has been stretched by gravity, its surface is wrapped in magnetic fields, and its interior holds matter that cannot exist anywhere on Earth. To understand how such a place begins, the path must first return to the final hours of a massive star, when a silent core of iron is growing heavier, colder in purpose, and unable to release one more breath of energy. The iron core begins as a quiet accumulation at the center of a star that has already spent nearly all of its useful fuel. Around it, layers of fusion continue in shells, one inside another, like thin fires burning at different depths. Hydrogen is still becoming helium far from the center. Deeper in, helium is becoming carbon and oxygen. Closer to the core, heavier nuclei are being assembled in faster and hotter reactions. The star has become a structure of nested furnaces, each one feeding the layer below. This arrangement does not last long. For most of its life, the star has lived in a balance between two opposing effects. Gravity pulls every layer inward. Fusion releases energy, heating the gas and creating pressure that pushes outward. Neither side wins completely. The star holds its shape because the inward and outward motions remain almost equal, changing only slowly over millions of years. A massive star reaches the end differently from a star like the Sun. Its greater weight presses the core to temperatures high enough to fuse elements that a smaller star can never reach. Hydrogen gives way to helium. Helium gives way to carbon. Carbon burning produces neon, sodium, and magnesium. Later stages form oxygen, silicon, sulfur, and other heavier nuclei. Each step needs a hotter and denser core than the one before it. The pace changes as the fuel grows heavier. Hydrogen burning may continue for millions of years. Helium burning lasts much less. Carbon burning may occupy only centuries. Neon burning can pass in about a year. Oxygen burning may continue for months. Silicon burning, the final major stage, may last only days. The star does not notice time as a human clock would. Its core responds only to pressure, temperature, and the supply of nuclei available for fusion. Still, the shortening sequence matters. A process that once unfolded over ages is now moving through its final stages almost too quickly to leave a long trace in the outer layers. Silicon burning does not produce one simple element in a single clean reaction. It creates a shifting collection of nuclei that are broken apart and rebuilt through many rapid interactions. Over time, this network settles toward iron group elements, especially nuclei near iron and nickel. These are among the most tightly bound forms of ordinary atomic matter. That binding is the problem. Fusion releases energy when light nuclei join and move toward a more tightly bound state. The small difference in mass is converted into energy, and that energy helps support the star. Iron lies near the point where this process stops being useful. Joining iron group nuclei into heavier ones does not provide the same outward supply of energy. It requires energy instead. The center now contains fuel that cannot keep the old balance alive. Silicon fusion continues in a shell around the iron-rich core, adding more material to it. The core grows heavier without becoming a new source of heat. It is not entirely cold, but it has become inert in the sense that matters most. It cannot produce enough energy through fusion to resist the increasing weight above it. At first, another form of pressure holds the core together. The electrons inside the dense matter have been forced into a compact range of space. Electrons belong to a class of particles called fermions, and identical fermions cannot occupy the same quantum state in the same place. As the core is compressed, the available low-energy states fill. Additional electrons must occupy states with greater momentum. That creates pressure even when ordinary thermal support is fading. This electron degeneracy pressure does not come from burning fuel. It is built into the quantum behavior of matter. A white dwarf can survive for an immense span of time because this pressure supports it after fusion has ended. The iron core of a massive star, however, is still being fed from above. Its mass continues to rise. There is a limit. As the core becomes heavier, the electrons move faster in response to the compression. Eventually, they approach the relativistic regime, where their speed is close to the speed of light. Beyond this point, adding more momentum does not increase their pressure rapidly enough to match the growing pull of gravity. The core moves toward the Chandrasekhar limit, roughly 1.4 times the mass of the Sun, though the exact threshold depends on temperature, composition, and rotation. The structure is now close to failure, but the collapse does not begin because of one isolated event. Several processes arrive together. The rising temperature creates energetic photons capable of breaking iron group nuclei apart. This process, called photodisintegration, absorbs energy from the core. Nuclei assembled through earlier stages of fusion are separated into lighter pieces, including alpha particles and individual protons and neutrons. The reaction removes pressure rather than adding it. At the same time, electrons are captured by protons in atomic nuclei. An electron and a proton combine to form a neutron, while a neutrino carries away part of the energy. The number of free electrons falls. Since those electrons were providing much of the degeneracy pressure, their disappearance weakens the support further. The core begins to contract. Contraction raises the density, which increases electron capture. More electron capture removes more pressure, allowing faster contraction. Photodisintegration continues to drain energy. The process feeds itself. What had been a stable core, only moments earlier, enters a runaway collapse. The outer regions of the star remain vast. Light from the surface still crosses space. The atmosphere has not yet had time to respond. Deep below, however, the center is falling inward at thousands of kilometers per second. Before collapse, the iron core is comparable in size to Earth. Within less than a second, its central region contracts toward the dimensions of a city. The distance between nuclei shrinks. Electron clouds no longer retain their familiar form. Matter passes through densities that no ordinary material can survive. Neutrinos are produced in immense numbers as electrons continue to combine with protons. Under normal conditions, a neutrino can pass through a planet with little chance of interacting. Inside the collapsing core, the density eventually becomes so high that even these weakly interacting particles are briefly trapped. They scatter through matter, approaching nuclear density, carrying energy but no longer escaping freely. The collapse continues until the nuclei have been pressed so closely that their boundaries lose their usual meaning. Neutrons dominate the composition. The inner core becomes stiff as neutron degeneracy pressure, and the short-range repulsion of the strong nuclear force rise sharply. For a fraction of a moment, the inward motion stops. The central core overshoots its new equilibrium and rebounds slightly. Matter still falling from above strikes this suddenly stiffened region. A shock wave forms and begins moving outward. It carries the possibility of an explosion, though not yet the certainty of one. As the shock passes through the infalling layers, it spends energy breaking apart heavy nuclei. It slows. The newborn neutron star remains hidden inside the collapsing star, hot, compact, and filled with trapped neutrinos. Around it, the stalled shock waits in dense matter, while material continues to fall inward. The star has reached a narrow interval between collapse and release. Its long life of fusion is over. The iron core is gone. In its place sits the beginning of something much smaller, much denser, and governed by a different set of physical limits. The stalled shock does not remain alone. Beneath it, the newborn neutron star is still changing, still releasing the energy of collapse in forms that ordinary stars never produce. Most of that energy leaves as neutrinos. In only a few seconds, the collapsing core releases more energy in neutrinos than the sun will radiate as light during its entire lifetime. Nearly all of the gravitational energy liberated by the collapse is carried away by these particles. At first, even neutrinos are trapped. The density inside the core is so high that they scatter again and again from neutrons, protons, and nuclei. Their path outward becomes a slow diffusion through matter compressed near nuclear density. The journey may take seconds, which is long compared with the collapse itself. Those few seconds matter. The shock wave formed at core bounce begins with great energy, but it loses much of that energy as it travels outward. Heavy nuclei in the infalling material are broken apart into protons and neutrons. Each breakup consumes energy. The shock weakens. Matter continues falling inward from the layers above, pushing against it. Without another source of energy, the shock would fade. The outer star would continue collapsing. The newly formed neutron star might gain enough mass to become a black hole. The neutrino flow changes the outcome. A small fraction of the neutrinos passing through the region behind the stalled shock is absorbed by matter there. The fraction is modest, yet the total neutrino energy is so large that even a small transfer can alter the entire star. Protons and neutrons absorb neutrinos and antineutrinos, heating the surrounding material. Convection begins. Hotter matter rises, while cooler matter falls closer to the neutron star. Large plumes form. The shock surface bends and shifts rather than remaining a perfect sphere. These motions keep matter in the heating region longer, giving it more time to absorb energy from the neutrino stream. Modern simulations show that this stage is not a simple outward push. It is a turbulent interaction involving convection, falling material, neutrino heating, and instabilities in the shock itself. The stalled front may oscillate. One side expands, while another side retreats. Dense streams continue feeding the central remnant, even as other regions begin moving outward. Eventually, if enough energy is deposited, the shock revives. The outward motion strengthens and begins to cross the surrounding layers. Gas that had been falling inward is turned around. The pressure behind the shock rises. The star's outer regions are lifted away from the compact core and accelerated into space. This is the beginning of the visible supernova. The explosion is not powered mainly by the rebound alone. The bounce creates the shock, but neutrino heating and turbulent motion help sustain it. The broad picture is supported by increasingly detailed three-dimensional models. The shock moves through layers built over the star's lifetime. It passes silicon-rich material, oxygen-rich shells, carbon, helium, and finally hydrogen if the star has retained its outer envelope. Some layers are heated enough to undergo additional nuclear reactions. Others are swept outward before they can change much. The explosion does not leave the star unchanged in a neat, symmetrical way. Fingers of material push through neighboring layers. Dense knots form. Elements created near the center are carried outward. Lighter material can be driven inward in narrow streams. The final debris field preserves traces of this mixing for centuries. As the shock reaches the surface, the outer layers brighten. Radiation that had been trapped inside begins escaping. The star may become brighter than billions of ordinary stars for a brief period. The light grows, changes color, and then slowly fades as the expanding material cools. Behind that light is an expanding shell, moving at thousands of kilometers per second. The ejecta carry carbon, oxygen, silicon, sulfur, calcium, iron, and other elements into interstellar space. Some were formed during the life of the star. Others were assembled or transformed during the explosion. Much of the iron group material comes from radioactive nickel formed in the explosion, which later decays through cobalt into iron. The energy from those decays helps power the visible glow after the initial flash. Elements heavier than iron can form through neutron capture processes, though the exact contribution from core collapse supernovae depends on the conditions within each event. The explosion may also leave asymmetry in the central remnant. If more material is ejected in one direction than another, the neutron star receives a recoil in the opposite direction. Some are born moving at hundreds of kilometers per second. Rotation and magnetic fields are altered as well. The core inherited angular momentum from the original star, but the collapse concentrates it. Small differences in the motion of the infalling material can change the spin. Magnetic fields are compressed and twisted. In some remnants, these fields later become strong enough to shape the radiation, leaving the star. The explosion does not always remove every outer layer. Some material may fail to escape and fall back toward the center. This fallback can add mass to the neutron star. A modest amount changes its rotation and surface composition. A larger amount may push the remnant beyond the maximum mass that dense matter can support. Then, the neutron star disappears behind an event horizon. In other cases, the explosion clears the surrounding layers, leaving the compact object exposed within a growing cloud of debris. The young neutron star remains extremely hot. Its interior temperature is measured in tens of billions of degrees shortly after formation, while the surface begins cooling more quickly by releasing radiation and neutrinos. The earliest cooling is dominated by neutrinos escaping from the interior. Over time, photons from the surface become more important. The exact cooling rate depends on the particles and reactions allowed inside the star. Even here, the future behavior of the remnant is tied to the unknown details of dense matter. The atmosphere settles into a layer only centimeters or meters thick. Gravity separates elements rapidly, drawing heavier nuclei downward and leaving lighter material near the top. Hydrogen, helium, or carbon may remain at the surface, depending on what falls back and what the magnetic field permits. The surrounding supernova remnant continues expanding. Shocked gas glows in radio waves, visible light, and X-rays. Filaments trace the paths of material thrown outward. At the center, the neutron star may be difficult to see, hidden by debris or visible only as a faint X-ray source. Sometimes it announces itself through pulses. If the magnetic axis is tilted away from the rotation axis, beams of radiation sweep through space as the star turns. When one of those beams crosses Earth, telescopes detect a regular sequence of pulses. The object becomes a pulsar, not because it is switching on and off, but because its radiation is rotating in and out of view. The massive star is gone. Its outer layers are spreading through space, carrying newly mixed elements into future clouds of gas and dust. At the center remains a compact sphere, still cooling, still spinning, and still holding more mass than the sun inside the width of a city. The explosion has ended the life of the star. It has also revealed the remnant that the next stage of the journey must approach. The remnant left behind by the explosion is smaller than almost anything that once belonged to the star. Its diameter may be only 20 to 25 kilometers, yet its mass can exceed that of the sun. A city can be crossed in less than an hour. The sun is more than 1,000,000 kilometers wide. The neutron star gathers comparable mass into a sphere so small that its curvature would be obvious from any nearby point. This compression changes every familiar property of matter. The average density is close to the density inside an atomic nucleus. Near the surface, matter is less compressed. Deeper down, the density rises until nuclei are no longer separate objects in the ordinary sense. The entire star is layered, but even its least dense, solid regions are far beyond anything found naturally on Earth. A small piece of neutron star matter is often compared with mountains, cities, or fleets of ships. Such comparisons help only slightly. The material cannot be removed and placed on a table while remaining unchanged. Away from the pressure that created it, the structure would not stay intact. The image is still useful because it reminds the mind that this is matter after almost all internal space has been taken away. Gravity at the surface reflects that concentration of mass. A falling object would accelerate with a force hundreds of billions of times, stronger than the gravity felt at Earth's surface. No mountain could rise high. No loose material could remain loosely arranged. Even a tiny elevation would carry enormous weight. The star becomes nearly smooth. That smoothness is not perfect. The crust may still support small asymmetries, and those differences matter because the object rotates so quickly. A rise only centimeters high can contain enough mass to influence the star's motion and, in some cases, produce a continuous pattern of gravitational waves. The escape speed is much higher than on Earth. Matter leaving the surface would need to move at a large fraction of the speed of light. The star is not a black hole because light can still escape, but the path outward is deeply altered by gravity. Photons lose energy as they climb away. Their wavelengths become longer, shifting toward the red end of the spectrum. This gravitational redshift changes the radiation detected by distant telescopes. A spectral feature produced at the surface arrives weakened and stretched. By measuring that shift, astronomers can place limits on the relationship between the star's mass and radius. The same gravity bends light. A distant observer may see more than half of the neutron star's surface at once because rays from the far side curve around the compact object. A hot region rotating out of direct view does not vanish as quickly as it would on an ordinary sphere. Its light follows a bent path and remains visible near the edge. This changes the pulses from rotating hotspots. Their shape contains information about compactness. A smaller star of the same mass bends light more strongly. A larger one bends it less. Telescopes can compare the observed pattern with relativistic models and estimate the radius of an object that cannot be resolved as a disk. The young neutron star is also hot, though it no longer burns through fusion. Heat left, the surface may remain near 1,000,000 degrees, radiating mainly in X-rays rather than visible light. It does not look like a warm ember. To human eyes, a neutron star would be almost invisible. Its surface area is tiny compared with that of a normal star, and most of its radiation lies beyond the visible range. X-ray observatories reveal the heat that ordinary optical telescopes might miss. Temperature is not always uniform. Magnetic fields guide heat through the crust more easily in some directions than others. The magnetic poles may become hotter. Accreting matter can also strike limited regions and create bright spots. As the star rotates, these areas move in and out of view, producing pulses. Rotation is one of the clearest traces of the collapse. Before the core contracts, it already carries angular momentum. When its radius shrinks by hundreds of times, the rotation speeds up, much as a skater spins faster after drawing in their arms. A newborn neutron star may turn many times each second. Some older neutron stars, spun up by matter from companion stars, rotate hundreds of times per second. At the equator of the fastest known pulsars, the surface moves at a noticeable fraction of the speed of light. The object remains intact because gravity is strong enough to hold the material together. Even so, rotation changes its shape slightly, making the equator wider than the poles. The spin is not eternal. A rotating magnetic field carries energy away. Charged particles flow through the magnetosphere, and electromagnetic radiation leaves the system. The star gradually slows. For some pulsars, the loss is so regular that the timing of their pulses can be predicted over long periods with great precision. That regularity turns the star into a clock. Small departures from the expected timing reveal orbital companions, changes in the magnetosphere, motion of material inside the crust, or the passage of gravitational waves across the space between Earth and the pulsar. The compact remnant becomes useful not only as an object of study, but also as an instrument for measuring other parts of the universe. The magnetic field was strengthened during collapse. Field lines that once threaded a much larger core were drawn into a far smaller volume. Rotation and turbulent motion may amplify them further. A typical neutron star carries a surface field far beyond anything built in a laboratory. Near the magnetic poles, charged particles are pulled from the surface and accelerated along field lines. They emit radiation in regions above the poles. When the magnetic axis is tilted relative to the rotation axis, those regions sweep through space. This creates the lighthouse pattern of a pulsar. The beams are not simple narrow rays, and the exact emission mechanism remains an active subject of research. Plasma fills the magnetosphere. Electric fields accelerate particles. Radio waves, X-rays, and gamma rays can emerge from different heights. The pulse, seen from Earth, depends on geometry as much as power. Some neutron stars possess magnetic fields thousands of times stronger than those of ordinary pulsars. These objects are called magnetars. Their magnetic energy can twist the crust and stress the interior. Sudden changes may release bursts of X-rays and gamma rays. Even here, the object remains compact and almost silent in visible light. Its presence is known through timing, spectra, heat, and changes in brightness. Every measurement arrives from a sphere too small to resolve directly and too distant to approach. The star must be reconstructed from the way it bends light, loses heat, slows its rotation, and shapes the plasma around it. The broad outline is now clear. The remnant is city-sized, heavier than the sun, hot enough to shine in X-rays, compact enough to bend its own light, fast enough to turn hundreds of times each second, and magnetic enough to control charged particles far above its surface. The next question lies beneath those observable properties. Such an object should still be collapsing under its own weight. Something inside must resist gravity at every moment, without fuel, without combustion, and without rest. The pressure holding a neutron star together does not come from burning fuel. There is no central furnace replacing what the iron core once had. The support comes from the quantum behavior of matter itself and from the way particles respond when gravity forces them into a space that is already full. Neutrons belong to a family of particles called fermions. Electrons and protons belong to the same family. Fermions obey the Pauli exclusion principle, which states that two identical fermions cannot occupy the same quantum state in the same place at the same time. The wording sounds simple. Its effect is not. Inside ordinary matter, electrons arrange themselves into layers of allowed states around atomic nuclei. The lowest states fill first. When those are occupied, later electrons must settle into higher ones. This arrangement shapes the periodic table, chemical bonds, and the firmness of the objects around us. In a neutron star, the same rule applies under far greater compression. Neutrons are packed so closely that the lowest available momentum states are filled. Any additional neutron must occupy a state with greater momentum. As gravity tries to reduce the star's volume, the neutrons are forced into an even broader range of high momentum states. The result is pressure. This neutron degeneracy pressure does not require heat. It remains even if the star cools. It does not depend on a continuing reaction, a supply of fuel, or a current flowing through the core. It is a direct consequence of the allowed states available to fermions. A normal star stays open because hot gas pushes outward. A white dwarf is held up mostly by electron degeneracy pressure. A neutron star is supported by a denser version of that quantum resistance, now involving neutrons rather than electrons. The transition is not merely a change of particle name. Neutrons are far heavier than electrons. Their behavior under confinement takes place at different densities and different energy scales. The matter can be compressed much further before neutron degeneracy pressure becomes dominant. Even this is only part of the support. At distances typical of an atomic nucleus, protons and neutrons interact through the strong nuclear force. This force binds nuclei together despite the electrical repulsion between protons. It is attractive over one range of distance, drawing nucleons together. At still shorter distances, the interaction becomes strongly repulsive. That short-range repulsion matters in a neutron star. Gravity forces the particles toward one another. The Pauli exclusion principle resists the overlap of quantum states. The repulsive part of the strong force resists the particles themselves being pushed too close. Together, these effects create the pressure that balances the weight of the star. The balance is described through an equation of state, a relationship between pressure, density, temperature, and composition. In familiar matter, such a relationship can be measured directly. Gas can be compressed in a laboratory. Metals can be heated. Liquids can be cooled and placed under pressure. Neutron star matter cannot be handled that way. The relevant densities exceed those reached in ordinary experiments by many orders of magnitude. Particle accelerators can produce dense matter for tiny fractions of a second, but the conditions are hot and rapidly changing. A neutron star contains matter that is comparatively cold on the scale of particle energies, held under pressure for thousands or millions of years. The equation of state must therefore be built from nuclear theory, laboratory measurements at lower density, and observations of real stars. A stiffer equation of state produces more pressure at a given density. Such matter can support a larger radius and a greater maximum mass. A softer equation of state gives less pressure, allowing the star to become more compact and lowering the mass at which collapse begins. The star's radius carries this information quietly. Two neutron stars with similar masses can have different radii if their internal matter responds differently to compression. A difference of only 1 or 2 kilometers is enough to favor some models and weaken others. Gravity complicates the calculation. In a Newtonian description, pressure pushes outward and mass pulls inward. In general relativity, pressure itself contributes to gravity. The very pressure supporting the star also adds to the source of space-time curvature. This makes the balance more delicate than it would be in a less compact object. The internal structure is found by solving the Tolman-Oppenheimer-Volkoff equations. These equations describe how pressure changes with depth inside a spherical relativistic star. Starting from a chosen central density and an equation of state, the calculation moves outward until the pressure falls to the surface value. Each choice produces a model star with a particular mass and radius. At lower central density, the star may have a modest mass and a somewhat larger radius. As the central density rises, more mass is added, and the structure becomes more compact. At first, pressure increases enough to preserve stability. Then a turning point appears. Beyond a certain central density, adding more matter no longer leads to a stable neutron star. The pressure cannot rise fast enough to match the stronger gravity. The object crosses from a stable branch of solutions into an unstable one. Collapse follows. The sharpness of that boundary is one reason neutron stars are useful tests of physics. Their existence already proves that dense matter can support at least the masses observed. Any theoretical equation of state that fails below those measured masses cannot describe nature correctly. Several neutron stars are known to contain close to 2 solar masses or more. That fact rules out many soft equations of state. Matter in the core must provide enough pressure to prevent collapse at those masses, even if new particles or new phases appear. Rotation can provide temporary help. A rapidly spinning neutron star carries centrifugal support, reducing the effective pull of gravity near the equator. This allows a rotating star to support slightly more mass than a non-rotating one. Differential rotation, where different layers turn at different rates, can add still more support for a short time. This state is not permanent. Magnetic stresses, gravitational waves, and internal viscosity redistribute angular momentum. As the star loses rotational support, a remnant that is already above the non-rotating mass limit may collapse. The event may leave little visible warning. There need not be a second supernova. The pressure balance simply fails. An event horizon forms around the compact object, and the detailed structure of the neutron star is hidden from the outside universe. Below that threshold, the star can remain stable for an immense time. It cools, it slows, its magnetic field changes, yet the quantum pressure does not run out. and the short-range nuclear repulsion does not need to be replenished. The star persists because matter has reached a form in which further compression is resisted by the rules governing particles themselves. This does not mean the interior is uniform. The same forces produce different arrangements as density rises from the surface toward the center. Near the outside, nuclei still exist in a lattice. Deeper in, neutrons escape from those nuclei. Farther down, even the distinction between separate nuclei disappears. The quantum wall is therefore not a single barrier located at one depth. It is distributed through the whole object, changing form from layer to layer. At the surface, the first traces of that structure begin beneath an atmosphere thinner than almost any terrestrial comparison. Below it waits a solid crust, built from nuclei that becomes stranger with every step downward. A neutron star can resist gravity only within a limited range of mass. The quantum pressure described earlier is powerful, and the repulsive part of the strong nuclear force adds further support, but neither effect grows without end. As more matter is added, the star becomes denser, its radius changes, and the balance moves closer to failure. The exact boundary is called the Tolman-Oppenheimer-Volkoff limit. It is not a single universal number that can be written down without qualification. Its value depends on the equation of state, which describes how dense matter responds when pressure rises far beyond anything available in terrestrial laboratories. This uncertainty is the central difficulty. If the equation of state is stiff, pressure rises quickly as density increases. The star can support more mass before collapsing. If the equation of state is soft, the pressure grows more slowly, the star becomes more compact, and the maximum stable mass is lower. Different microscopic models therefore produce different stars. Some models treat the core as matter made mostly of neutrons, with smaller fractions of protons, electrons, and muons. Others allow additional particles to appear at greater depth. Hyperons, meson condensates, or deconfined quarks may reduce the pressure at a given density. Repulsive interactions among those particles may restore part of it. Each possibility changes the mass and radius that the star can sustain. The heaviest observed neutron stars act as anchors in this uncertain landscape. Several pulsars have masses close to 2 times that of the Sun. Their masses can be measured with unusual precision when they orbit companion stars. Pulses arrive at regular intervals, but the orbit changes those arrival times. Relativistic effects add further shifts. By following the timing pattern over many years, astronomers can infer the masses of both objects. A theory that cannot support such stars is excluded. This has already removed many proposed equations of state. Any model predicting collapse below the mass of a well-measured pulsar cannot describe the full behavior of real neutron star matter. The observation does not reveal the exact composition of the core, but it places a firm lower boundary beneath the maximum mass. The upper boundary is more difficult. A neutron star that becomes too heavy may collapse quickly, leaving no long-lived object to measure. The final moment may be hidden behind an event horizon before much radiation escapes. Binary neutron star mergers provide another path. 2 neutron stars orbiting each other lose energy through gravitational waves. Their orbit shrinks over millions or billions of years. During the final seconds, the frequency rises rapidly. The stars distort under each other's gravity, collide, and form a remnant with a mass larger than either object had before. What happens next depends on the total mass, the equation of state, and the amount of rotational support. A remnant below the non-rotating maximum mass can settle into a stable neutron star. One above that limit may remain temporarily supported by rapid rotation. If the rotation is uniform, the object is often called supramassive. If different layers rotate at different rates, the support can be stronger for a shorter interval, producing a hypermassive neutron star. Neither state is guaranteed to last. Magnetic fields redistribute angular momentum. Turbulence and viscosity reduce differential rotation. Gravitational waves carry energy away. As those temporary supports weaken, the remnant may cross the stability boundary and collapse into a black hole. The first observed binary neutron star merger, GW170817, offered a rare view of this process. The gravitational wave signal measured the inspiral. A short gamma-ray burst followed. Telescopes then observed a kilonova, an expanding cloud powered by radioactive decay in neutron-rich material. The total mass of the system was about 2.7 times the mass of the Sun. The final remnant was not observed directly for long enough to reveal its structure. The available evidence suggests that it did not remain as a stable neutron star indefinitely. It may have survived briefly before collapsing, though the exact duration remains uncertain. That uncertainty contains information. If the maximum mass were far below the remnant mass, collapse would have occurred almost immediately. If it were much higher, a stable or long-lived remnant might have left a different electromagnetic signature. By comparing the observed light, gamma rays, gravitational waves, and ejected material with simulations, researchers place limits on the allowed maximum mass. The result is not one exact number. It is a narrowing interval. Current models generally place the maximum mass of a non-rotating neutron star somewhere above the heaviest measured pulsars and below values that would allow every merger remnant to remain stable. The precise location depends on how matter behaves at several times nuclear density. Rotation changes the boundary, but only temporarily. A rapidly spinning star is wider at the equator and receives centrifugal support. The maximum mass can rise above the non-rotating value. As the star loses spin, the extra support fades. Accretion can create the same quiet approach to collapse. In a binary system, gas may flow from a companion star toward the neutron star. Some of that material forms a disk. Friction heats the disk, producing X-rays, while matter gradually settles onto the compact surface. The star gains both mass and angular momentum. At first, the added rotation may help support the increased weight. Over time, however, the system can reach a state in which the star survives only because it is spinning rapidly. When accretion ends and the star begins to slow, the stability boundary moves inward. Collapse may then occur without a supernova. The event horizon forms around matter that had been visible only moments before. The surface, magnetic poles, crust, and interior layers disappear from external view. Radiation already traveling outward continues on its path, but no new signal can escape from inside the horizon. A disk can continue glowing. Magnetic fields outside the horizon may reconnect. Matter still falling inward can produce radiation before crossing. Yet the neutron star itself is gone, as an observable object. This sharp transition explains why the maximum mass matters so deeply. It separates two kinds of compact object with entirely different external structures. Below the limit, matter has a surface, a crust, magnetic poles, and internal motion. Above it, the same mass becomes hidden behind a horizon. No gradual layer lies between them. A neutron star can become smaller as mass is added, but it does not slowly turn into a black hole while remaining partly visible. Stability persists until the allowed balance is lost. Then collapse proceeds on a timescale measured in milliseconds. The equation of state determines how close the star stands to that boundary. Radius measurements, pulse timing, merger signals, and cooling behavior all contribute pieces of the same problem. None alone is enough. Together, they reduce the range of possible interiors. The mass limit is therefore not only a final number, it is a summary of everything hidden inside the star. It reflects the pressure of neutrons, the strength of nuclear interactions, the possible appearance of unfamiliar particles, and the curvature of spacetime produced by the star's own mass. Every heavy pulsar that remains stable places another condition on that hidden physics. The boundary has now been reached in theory, but the interior still has not been entered. Before the deepest uncertainties appear, the path begins at the outside, where the first layer is neither empty space nor solid ground, but a thin atmosphere pressed flat against a surface brighter in X-rays than in visible light. The outermost visible layer of a neutron star is not a surface in the ordinary sense. There is no soil, no loose stone, and no boundary that could be crossed by a step. What telescopes detect first is a layer of gas pressed so tightly against the star that the word atmosphere begins to feel misleading. This atmosphere may be only centimeters or meters thick. On Earth, air extends upward for many kilometers before fading into space. Here, gravity compresses the gas into a layer thinner than the paint on a large metal sphere. The pressure changes so rapidly with height that moving upward by a small distance can alter the density by an enormous amount. The composition depends on the history of the star. Hydrogen or helium may remain after the supernova. Carbon can appear if lighter elements have been burned or removed. In binary systems, fresh material may arrive from a companion and spread across the exterior. Gravity separates these elements quickly, drawing heavier nuclei downward, while lighter ones remain closer to the top. The sorting is efficient because the gravitational field is so strong. On a calm star, an atmosphere that begins mixed does not remain mixed for long. The particles settle by weight until the lightest available element dominates the outermost region. The atmosphere is also hot. A young neutron star can carry a surface temperature of 1,000,000 degrees or more. Older stars cool, though some are reheated by accretion, magnetic decay, or motion inside the crust. At these temperatures, atoms may be ionized, leaving nuclei and electrons moving through a dense plasma. Most of the escaping light lies in X-rays. Those X-rays carry more than brightness. Their spectrum changes with temperature, composition, magnetic field strength, and gravity. A hydrogen atmosphere produces a different pattern from a carbon atmosphere. Strong magnetic fields alter the allowed energy states of electrons and reshape the emitted radiation. Gravity stretches every photon on its way out. The observed spectrum is therefore a layered message. It contains traces of the gas itself, the compactness of the star below, and the path the light has taken through curved spacetime. There is still uncertainty. The same data can sometimes be matched by more than one atmospheric model. A star that appears small under one assumed composition may appear larger under another. The surface magnetic field can introduce additional structure. Distance estimates and interstellar absorption also affect the result. Even so, the atmosphere is one of the few parts of a neutron star that can be studied through direct radiation. Beneath it lies what is usually called the surface. The word suggests a clean division, but the transition is gradual. Gas becomes denser, electrons become increasingly degenerate, nuclei arrange themselves more regularly. At some depth, matter behaves like a solid crust. There is no familiar ground. A solid object on Earth keeps its shape because electromagnetic forces hold atoms apart at ordinary density. The crust of a neutron star is solid for a different reason and under a different pressure. Atomic nuclei remain present, but they are packed into a crystalline lattice and immersed in a sea of electrons. Near the top, the nuclei may resemble iron group elements. Deeper down, increasing pressure forces electrons into protons, turning some protons into neutrons. The nuclei become progressively richer in neutrons. Their forms would be unstable under terrestrial conditions, yet the pressure of the star keeps them together. The result is matter that is recognizable in outline but not in scale. A lattice still exists. Electrons still move between nuclei. Electrical and thermal conduction still occur, yet every spacing is smaller, every pressure is larger, and the gravitational field allows almost no relief. The surface is also curved more strongly than its small size might suggest. Light emitted nearly sideways can bend upward and escape. Radiation from regions beyond the ordinary horizon can reach a distant observer. A telescope may therefore receive light from much more than the hemisphere directly facing it. This effect softens the rise and fall of X-ray pulses from hotspots. A bright region remains visible even after rotation carries it partly around the far side. The amount of bending depends on the ratio of mass to radius, so the pulse shape becomes a tool for measuring the star. A smaller radius means stronger bending. A larger radius means less. The NASA instrument NICER uses this principle by recording the arrival times and energies of X-ray photons from rotating neutron stars. Models reproduce the motion of hot spots across the curved surface. By comparing those models with the observed pulse pattern, researchers estimate the mass and radius. The method does not photograph the surface. It reconstructs its geometry from light. That distinction matters. Every map of a neutron star is an inference built from timing, spectra, polarization, and relativistic effects. No image shows mountains or cracks in the way a camera sees the moon. The exterior is too small and too distant. Magnetic fields add another layer of complexity. Heat does not move through the crust equally in all directions when the field is strong. It travels more easily along magnetic field lines than across them. Some regions cool more efficiently, others remain warmer. The poles may glow more brightly, while broad areas between them emit less. A magnetar can have an even less uniform surface. Magnetic stresses twist the crust. Energy stored in the field can be released as heat. The X-ray glow may come from several patches that shift slowly over time. The surface is therefore not a single temperature, neither is it perfectly smooth. Gravity suppresses large elevations, but the crust may support small deformations. A feature only a few centimeters high can contain a great amount of mass. Such asymmetry matters when the star rotates quickly, because a non-spherical object can disturb space-time in a repeating pattern. Continuous gravitational waves from these tiny distortions have not yet been firmly detected from an isolated neutron star. Searches continue because even a very small departure from symmetry could produce a measurable signal if the star is close enough and spins fast enough. The exterior may also change suddenly. Stress accumulates as the star slows, as magnetic fields evolve, or as the interior shifts. The crust can crack or rearrange. On a magnetar, this movement may accompany bursts of X-rays and gamma rays. The event is often described as a starquake, though the motion is not identical to an earthquake on a rocky planet. The crust does not float above a molten mantle. It is part of a compact object whose deeper layers include superfluid matter and magnetic structures. A disturbance in one region can couple to the rest of the star. The boundary called the surface is therefore only the beginning of the interior. Above it, a thin atmosphere filters the escaping X-rays. Within it, nuclei form a rigid lattice. Beneath it, pressure drives matter toward compositions that cannot survive anywhere on Earth. The star presents no ground, only a sequence of increasingly compressed states. A little farther down, the nuclei reach a limit of their own. They become so rich in neutrons that the excess can no longer remain bound. The first free neutrons begin to appear between the lattice sites, and the solid crust enters a new phase. Before the first free neutrons appear, the crust passes through a region where matter still keeps the outline of an atomic nucleus. The nuclei are no longer ordinary. Pressure has changed their balance of protons and neutrons, and the electrons around them no longer belong to individual atoms. Even so, the matter remains arranged. The arrangement is crystalline. Near the top of the crust, iron group nuclei occupy regular positions in a lattice. Electrons move through the structure as a highly degenerate gas, carrying heat and electrical current. Deeper down, electron capture reduces the number of protons in each nucleus. The nuclei grow heavier and more neutron-rich, while the lattice spacing becomes smaller. The pattern survives because the charged nuclei repel one another, while the surrounding electrons keep the material electrically neutral. Each nucleus settles into a position where the forces from its neighbors balance. The result resembles a metal only in the broadest sense. Its density, pressure, and binding are far beyond any metal that can exist on Earth. The lattice is often described as body-centered cubic, one of the common arrangements found in ordinary crystals. That familiar geometry appears in an unfamiliar setting. A structure seen in laboratory metals is repeated inside a star, where gravity has compressed matter to the edge of nuclear change. The crust is not perfectly pure. Its exact composition depends on how the neutron star formed and whether it has accreted matter from a companion. A crust left from the original collapse may follow one sequence of nuclei. A crust rebuilt by accretion follows another, as fresh material is buried and transformed by rising pressure. Those differences matter. Impurities scatter electrons and reduce thermal conductivity. A cleaner lattice carries heat more efficiently. Cooling observations of neutron stars after periods of accretion suggest that some crusts conduct heat very well, implying a relatively ordered structure. Other stars may contain more disorder, especially in the deepest layers. The strength of this crystal is one of its most unusual properties. On Earth, a solid breaks when defects move through its lattice and allow layers of atoms to slide past one another. Neutron star matter is held under such pressure, and the electrostatic interaction between nuclei is so strong that much greater stress is required. Computer simulations suggest that the crust can withstand a strain approaching 1/10 of its original shape before failing. That value is enormous for a solid. Steel begins to deform under far smaller strain. Rock fractures earlier still. The neutron star crust remains rigid, while forces build across kilometers of compressed material. It can store elastic energy for years before a local region shifts. This does not make the crust indestructible. It makes each failure more significant. As the star cools, its internal structure changes slightly. As it loses rotational energy, the shape preferred by gravity becomes more spherical. The solid crust cannot always adjust smoothly. Magnetic fields also pull and twist the lattice, especially in magnetars, where field strengths can dominate the mechanical stress. Slow changes accumulate. At some point, a section of the crust yields. The motion may be a crack, a plastic flow, or a sudden rearrangement spread across a broader region. The word starquake is used because the event releases stored stress, but the physical process is still being studied. The material is not an ordinary brittle rock, and the intense pressure may prevent open fractures from forming in the familiar way. A small displacement can still release a large amount of energy. In magnetars, crustal motion may disturb the magnetic field above the surface. Twisted field lines can reconnect or rearrange, accelerating particles and producing bursts of X-rays and gamma rays. The crust and magnetosphere respond together, so it is difficult to separate the first cause from the later release. Some bursts last only fractions of a second. Others are followed by longer tails of radiation modulated by the star's rotation. The repeating pattern reveals the turning object beneath the fading light. The crust also shapes how the neutron star rings. After a strong disturbance, different regions may oscillate. Some modes involve the crust shearing sideways, while others include motion in the fluid interior. Quasi-periodic variations have been observed in the X-ray tails of giant magnetar flares. These signals may be connected with global oscillations, though identifying each mode remains difficult. The idea resembles seismology, but the instrument is far away. No detector touches the surface. The oscillation must alter the escaping radiation enough to leave a pattern in the data. Magnetic fields couple the crust to the magnetosphere, and the fluid core can change the frequencies. A simple vibration of the solid shell becomes a motion of the entire compact star. The lattice may carry another quiet signature. A rapidly rotating neutron star emits no continuous gravitational waves if its mass is distributed with perfect symmetry around the rotation axis. The moment a persistent asymmetry appears, the rotating gravitational field changes in a repeating way. Space-time carries that changing pattern outward as waves. The deformation can be extremely small. A ridge only centimeters high may be called a mountain, though it bears little resemblance to a terrestrial peak. The surface gravity is too strong for large relief. What matters is not height alone, but the amount of mass displaced away from perfect symmetry. The crust's high breaking strain allows it to support a larger asymmetry than weaker material could. The maximum size depends on the star's mass, radius, temperature, composition, and magnetic field. Even the strongest crust remains constrained by gravity. Searches for continuous gravitational waves target known pulsars and broader regions of the sky. So far, no isolated neutron star has produced a confirmed continuous signal. The upper limits already restrict how distorted some nearby pulsars can be. Silence has value here. A non-detection means the star cannot possess every possible combination of mountain size, orientation, and distance. As detectors improve, the permitted distortions become smaller. The crust is being tested through the absence of a signal as well as through the presence of glitches and flares. Magnetic fields can create asymmetry below the surface too. A strong internal field may stretch the star along one direction or flatten it along another. The exterior field measured from pulsar timing may reveal only part of the total magnetic energy. Hidden toroidal fields inside the crust can alter the shape without producing an equally obvious surface signature. The crust is therefore both a shell and a record. Its nuclei preserve the compression history of the star. Its impurities affect cooling. Its strength controls how stress accumulates. Its failure can disturb the magnetosphere. Its shape may write a faint, continuous pattern into spacetime. Yet the lattice does not continue unchanged all the way down. Pressure keeps increasing with depth. Electron capture drives the nuclei toward more neutron-rich combinations. Each nucleus holds an expanding excess of neutrons until the final bound states are filled. Beyond that point, another neutron cannot remain confined without raising the energy of the system too far. The excess begins to escape. Free neutrons appear in the spaces between nuclei, while the crystal remains present. The star crosses the neutron drip boundary, and the crust becomes a mixture of solid order and a fluid that can move through it without ordinary friction. The neutron drip boundary is not a sharp wall made of different material. It is a change in what the nuclei can hold. Above this depth, neutrons remain bound inside increasingly heavy nuclei. Each added layer of pressure favors nuclei with a larger neutron excess. The electrons around them continue to be captured by protons, reducing the electric charge and increasing the number of neutrons. At some point, however, the last available bound states are filled. Another neutron no longer fits comfortably inside the nucleus. The excess begins to leak out. This transition occurs at a density of roughly 400 billion grams per cubic centimeter, though the exact value depends on the nuclear model. The crystalline lattice remains. Neutron-rich nuclei still occupy ordered positions. Electrons still move through the structure. What changes is the appearance of a new component. Free neutrons filling the space between the nuclei. The inner crust has begun. The word free needs care here. These neutrons are not drifting through empty space like dust in a room. The region is already crowded with matter and quantum fields. They move through a periodic lattice of nuclei and interact with one another through the strong nuclear force. Their behavior is collective. At first, only a small fraction of the neutrons are unbound. Deeper down, the fraction grows. The nuclei become larger, more distorted, and increasingly immersed in a surrounding neutron fluid. The distinction between matter inside the nucleus and matter outside it becomes less obvious with depth. A crystal suggests rigidity. A fluid suggests motion. The inner crust contains both. The lattice of nuclei behaves as a solid framework. The free neutrons form a quantum liquid that can move through that framework. The two components occupy the same volume, but do not respond in the same way to rotation, stress, or temperature. The neutron liquid is expected to become superfluid. Superfluidity begins when neutrons form pairs. Individual neutrons are fermions and obey the Pauli exclusion principle. At sufficiently low temperature, an attractive interaction can bind two neutrons with opposite momenta and spin into a Cooper pair. The pair behaves collectively like a boson, allowing many pairs to settle into the same quantum state. The result is a fluid with no ordinary viscosity. The neutron star is still hot by terrestrial standards. Its interior may remain at millions of degrees, yet temperature is meaningful only relative to the energy scale of the particles involved. For dense neutron matter, the critical temperature for pairing may reach hundreds of millions of degrees. A mature neutron star can therefore be cold enough for superfluidity, even while remaining far hotter than any furnace on Earth. The motion of a superfluid differs from the motion of normal liquid. A normal fluid can rotate as a whole. A superfluid carries rotation through quantized vortices. Each vortex is a narrow line around which the fluid circulates, and each one carries a fixed amount of angular momentum. A rotating neutron star may contain an enormous array of these lines. They run through the superfluid roughly parallel to the rotation axis. Their number depends on the spin rate. A faster star requires more vortices. As the star slows, the superfluid must reduce its total vortex count, which means vortices need to move outward and eventually leave the rotating region. The solid crust does not always allow that motion easily. Vortices interact with the nuclei in the lattice. In some regions, a vortex lowers its energy by passing through or near a nucleus. It becomes pinned. The line is held in place even while the crust gradually loses angular momentum through electromagnetic radiation. The crust slows first. The pinned superfluid keeps more of its original rotation. A difference in angular velocity begins to build between the two components. The effect is small in fraction but large in stored angular momentum because the superfluid contains an immense amount of mass. The inner crust becomes a hidden reservoir. The image resembles water moving through a forest of fixed columns, but the comparison breaks quickly. The system is quantum mechanical. The vortices are topological structures. The lattice is nuclear matter, and the coupling between them depends on microscopic energies that remain difficult to calculate precisely. As the lag grows, the force acting on the pinned vortices increases. Eventually, some can no longer remain fixed. They unpin and move. Their motion can disturb nearby vortices, allowing a local release to spread through a larger region. Angular momentum is transferred to the crust. The surface rotation increases suddenly. Telescopes detect the change as a pulsar glitch. The event may last less than the time required to resolve it directly. A pulsar that had been slowing in a predictable way arrives slightly early. Its period has shortened by a tiny amount. Afterward, part of the change remains, while another part relaxes over days, months, or longer. That recovery contains information about the interior. Different components recouple on different timescales. Some parts of the superfluid respond quickly. Others remain partly separated. The observed return toward the previous spin-down trend allows models to estimate how much moment of inertia belongs to each region. The largest glitches suggest that a significant reservoir is involved. For many years, the inner crust superfluid seemed sufficient. Later calculations introduced a complication called entrainment. The free neutrons are not completely independent of the lattice. Their quantum waves interact with the periodic nuclear structure, causing some of their motion to be carried along with the crust. This reduces the amount of freely moving superfluid available to power a glitch. If entrainment is strong, the inner crust alone may not contain enough angular momentum for the largest observed events. Part of the superfluid in the outer core may also need to participate. The exact answer depends on the star's mass, the properties of the crust, and the strength of the coupling. A glitch is not only a timing irregularity, it is a constraint on how much superfluid exists, how vortices move, how strongly they pin, and how the crust connects to the core. Repeated glitches from the same pulsar allow those constraints to improve over time. No telescope sees the vortices themselves. Their presence is inferred from the way the surface turns. The inner crust also affects heat transport. Superfluid pairing changes the heat capacity of neutron matter and alters the neutrino reactions available at a given temperature. When pairs form or break, they can emit neutrinos, briefly accelerating cooling. Observations of young neutron stars have been used to test these ideas. The cooling behavior of the compact object in Cassiopeia drew attention because some measurements suggested a rapid temperature decline over a decade. One proposed explanation involved the onset of neutron superfluidity in the core, though the size of the decline and its interpretation remain debated. The important point is the connection between microscopic pairing and the slow fading of X-ray light from a distant star. In the inner crust, Solid and fluid states coexist without blending into an ordinary mixture. The lattice stores stress. The neutron superfluid stores angular momentum. Electrons carry heat and current. Each component responds differently. Yet all are held within the same compact sphere. Deeper down, the nuclei become larger and less spherical. Their surfaces begin to touch. The competition between nuclear attraction and electric repulsion reshapes them into rods, sheets, and connected voids. The lattice is approaching its final forms. The superfluid beneath the crust does not rotate as a smooth, featureless body. Its motion is divided among countless quantized vortices, each one carrying a fixed unit of circulation. Together they form an ordered array aligned, on average, with the rotation axis of the star. These vortices are extraordinarily thin. Their cores are microscopic, yet their influence extends through the surrounding superfluid. A single line may pass through a large fraction of the inner crust, threading a region where nuclei, electrons, and free neutrons coexist. The star's visible rotation depends partly on how these invisible lines move. As the neutron star loses rotational energy, the solid crust slows. The magnetosphere carries energy away through radiation and charged particles. The superfluid cannot simply reduce its rotation everywhere at once. It must move vortices outward. That motion is not free. The nuclear lattice creates a landscape of preferred positions. In some regions, a vortex lowers its energy by passing near a nucleus. In others, the surrounding neutron density makes a different arrangement more favorable. The exact pattern depends on the composition of the crust and on how neutron waves overlap with the lattice. A vortex can become pinned. While pinned, it cannot move outward at the rate required by the gradual spin-down of the crust. The superfluid continues rotating slightly faster than the solid exterior. The difference is small, but it grows over months or years. Stress accumulates in silence. The increasing lag produces a force on the vortex lines. At first, the pinning sites hold. Later, a group of vortices begins to move. One unpinning event changes the local flow and can disturb neighboring lines. The release may spread as an avalanche through part of the superfluid. Angular momentum then moves from the faster interior to the slower crust. The surface speeds up. A radio telescope does not see the transfer itself. It detects a pulse arriving earlier than predicted. The rotation period has shortened by a tiny fraction. That sudden shift is called a glitch. Some glitches are small enough to alter the period by less than 1 part in a billion. Others are much larger. The Vela pulsar is known for events in which the rotation frequency increases by roughly 1 part in a million. For an object with the mass of a star, that modest fraction represents an immense redistribution of angular momentum. The glitch can occur faster than observations resolve. In several well-studied pulsars, the rise time is constrained to seconds or less. This rapid change suggests that at least part of the interior couples to the crust very efficiently once the vortices begin moving. The recovery is slower. After the sudden spin-up, the pulsar may relax through several overlapping stages. One component returns in hours. Another changes over days. A third may continue recovering for months or years. Each timescale points to a region with a different coupling strength. The star is not behaving as one rigid sphere. The crust, the charged particles in the core, and different superfluid regions exchange angular momentum at different rates. A glitch briefly exposes those hidden connections. This makes pulsars a form of remote seismology. On Earth, the interior is inferred from waves passing through rock. In a neutron star, the evidence arrives as timing. The frequency jump, the recovery curve, and the long-term change in spin-down rate all constrain the matter below the surface. The interpretation is not simple. Vortex pinning is expected in the inner crust, but calculations disagree on its strength. The nuclei are not isolated spheres. Their surrounding neutron fields overlap. The free neutrons move through the periodic lattice as quantum waves. This interaction modifies the fraction of superfluid that can flow independently. Some neutrons that appear free are partly carried with the crust. Their momentum does not point in the same direction as their velocity in the ordinary way. The lattice alters their motion, reducing the effective reservoir available for a glitch. Early models often treated nearly all dripped neutrons as independent. Stronger entrainment means fewer of them can transfer angular momentum freely. In that case, the inner crust may not be enough to explain the largest glitches. The outer core may take part. Superfluid neutrons are expected there as well, but the core contains superconducting protons and magnetic flux tubes. Vortices moving through that environment can interact with magnetic structures. Depending on the strength of the coupling, some core superfluid may join the sudden transfer, while other regions remain separated. This possibility changes the usual picture. A glitch may not be confined to a thin shell beneath the crust. It may involve a larger fraction of the star, with different layers responding in sequence. The first change can be rapid, while later adjustments continue as vortices repin and the interior returns toward equilibrium. Observations are beginning to resolve more of that sequence. High-cadence radio monitoring can follow a pulsar before, during, and after a glitch. X-ray telescopes can search for changes in surface temperature or pulse shape. In some objects, the glitch is accompanied by altered radiation from the magnetosphere. In others, the timing changes without any obvious brightening. The difference is useful. A quiet glitch may be driven mainly by internal superfluid motion. A radiatively active event may involve the crust or magnetic field more directly. The same term covers several physical pathways that can overlap. Magnetars provide another version. Their strong internal fields place stress on the crust. A sudden magnetic rearrangement may trigger crustal motion, which then disturbs the superfluid vortices. The resulting timing event can include a spin-up, a spin-down, or a more complicated change. The interior and exterior are coupled both ways. A movement in the crust can change the magnetosphere. A change in magnetic stress can alter the crust. Vortex motion below may follow. Each observed event is therefore a partial record of several components responding together. A major uncertainty lies in the microscopic details. Researchers need to know how strongly vortices pin to nuclei, how easily they cut through flux tubes, how thermal motion assists unpinning, and whether vortex avalanches behave collectively across large distances. These questions are studied with nuclear theory, superfluid models, and simulations that can cover only limited scales. No single calculation spans the entire star. A vortex core is microscopic. A glitch can involve kilometers of matter. Connecting those scales remains difficult. Yet the pulsar performs the experiment repeatedly, offering another timing curve each time the hidden reservoir shifts. Some stars glitch often, others rarely do. Some show many small events. Others remain quiet for years and then change suddenly. Age, temperature, magnetic field, and internal composition may all influence the pattern. The distribution itself becomes evidence. A warmer superfluid may allow vortices to creep gradually between pinning sites, releasing stress in small amounts. A colder region may store more lag before a collective unpinning. Stronger magnetic coupling can shorten recovery times. A thicker crust can hold a larger reservoir. None of these factors acts alone. The pulse train reaching Earth may appear simple, one flash after another with almost perfect regularity. Beneath that regular signal is a rotating quantum fluid divided into vortices, pinned to a solid lattice, exchanging momentum across layers that cannot be seen. A glitch is the moment that hidden structure moves. Deeper still, the lattice begins to lose its familiar form. Nuclei stretch into rods, merge into sheets, and leave connected voids. The vortices continue through this changing landscape as the inner crust approaches the nuclear pasta layer. Near the base of the inner crust, the familiar picture of separate nuclei begins to fail. The pressure is too high, the neutron fluid is too dense, and the distance between neighboring nuclei has become too small for each one to remain an isolated sphere. The matter does not turn into a uniform liquid all at once. Instead, it passes through a sequence of shapes. These structures arise from a competition between two forces. The strong nuclear force favors keeping protons and neutrons close together. Electrical repulsion pushes the positively charged protons apart. At lower density, the balance produces separate nuclei, surrounded by electrons and free neutrons. At higher density, the nuclei grow, touch, and merge. The lowest energy arrangement may no longer be spherical. Some calculations produce long cylindrical structures. These are often called spaghetti. At slightly greater density, the cylinders merge into broad sheets known as lasagna. Other phases contain cylindrical holes running through nuclear matter, followed by rounded voids enclosed inside it. The names are informal, the physics is not. Each shape represents matter, finding a way to reduce its total energy, while living under pressure close to the point where nuclei disappear entirely. The exact sequence depends on the number of protons, the strength of nuclear interactions, and the density at each depth. Different models do not always predict the same order. Some find several distinct phases, others find fewer. The transitions may be smooth, with rods bending into sheets and sheets merging into connected networks, rather than changing at one clean boundary. Temperature and defects can complicate the arrangement further. No sample of nuclear pasta has ever been collected. The evidence comes from nuclear theory and large computer simulations. These calculations follow thousands or millions of particles interacting inside a small region meant to represent part of the crust. The simulation box is repeated in every direction, approximating matter that extends far beyond the calculated volume. Even this limited task is difficult. The strong force acts over very short distances. Electrical repulsion reaches much farther. Neutrons move through and around the structures as a quantum fluid. A realistic calculation must balance all of these effects without covering the full size of the star. Despite differences in method, many independent models produce some form of non-spherical nuclear matter near the crust core boundary. The broad idea is therefore widely taken seriously. Even though the precise geometry remains uncertain, the structures can be more disordered than their names suggest. Spaghetti may bend, branch, or join neighboring strands. Lasagna may contain holes, curves, and bridges between sheets. Defects can form where regions with different orientations meet. The result may look less like carefully arranged food and more like a frozen network of membranes and tunnels. This disorder changes the way the material behaves. Electrons moving through the layer can scatter from defects. Heat may travel more easily in one direction than another. Electrical conductivity can vary with the orientation and purity of the structures. These differences influence how the crust cools and how magnetic fields evolve. A highly ordered pasta layer could conduct heat efficiently. A disordered one could trap heat longer and slow its passage toward the surface. Cooling observations offer one possible test. In an accreting binary, matter from a companion star falls onto the neutron star and is buried. Compression drives nuclear reactions in the crust, releasing heat. When accretion stops, the crust begins cooling back toward the temperature of the core. X-ray telescopes follow that decline. The speed of cooling depends on thermal conductivity, heat capacity, and the thickness of each layer. If nuclear pasta strongly scatters electrons, the deepest crust can act as an insulating blanket. Some cooling curves have been interpreted as allowing or favoring such a low conductivity region, though the result is not unique. Other uncertainties can produce similar behavior. The amount of heating during accretion, the composition of the atmosphere, the core temperature, and the length of the accretion episode all affect the observed light. Nuclear pasta cannot be identified from one cooling curve alone. The layer may also be exceptionally strong. Earlier estimates suggested that the outer crust was already the strongest known solid. Simulations of nuclear pasta indicate that its connected structures may resist deformation even more effectively in some directions. Large regions must move together before the network can fail. The strength depends on geometry. A sheet can resist force differently when pushed along its surface than when pulled across it. Rods can bend more easily in one direction than another. The material may be elastic in some ways and softer in others. This anisotropy can shape how stress travels through the crust. A magnetic field twisting the star does not load every region equally. Stress may concentrate where pasta domains meet or where one structure changes into another. A failure can begin in those weaker zones and then spread into surrounding material. In a magnetar, such movement may help trigger a larger magnetic rearrangement. The pasta layer sits near the base of the crust, where it can connect the rigid exterior to the fluid core. This position makes it important even if the layer is only a few hundred meters thick. A disturbance crossing it must pass from one kind of matter into another. Some oscillations may be trapped above the boundary. Others can enter the core. The way nuclear pasta transmits shear motion affects models of magnetar flares and crustal vibrations. If the layer is softer than expected, certain oscillations may remain confined to the outer crust. If it is strongly connected, the crust and core may respond more like one object. The same layer can influence gravitational waves. A non-axisymmetric deformation in the crust must be supported against gravity. The maximum distortion depends partly on the breaking strain of the deepest material. Strong pasta could allow a larger mountain. A weak or highly disordered layer might yield earlier. The effect remains hidden until the star rotates. If the distortion survives, it changes the gravitational field in a repeating pattern. Continuous wave searches then place upper limits on how large that deformation can be. Nuclear pasta may also affect neutrinos. Neutrinos leaving the hot interior can scatter from the ordered structures. When the wavelength of a neutrino is comparable to the spacing between sheets or rods, scattering can become enhanced. This can alter the rate at which a young neutron star loses heat. The effect is most important early in the star's life, while the interior remains hot enough for neutrino emission to dominate cooling. Later, photon emission from the surface becomes more visible, but the thermal history still carries traces of what happened deeper inside. The pasta layer is therefore involved in several processes at once. It can shape cooling, magnetic evolution, crustal motion, vortex pinning, and gravitational wave emission. Yet none of these effects has provided a direct detection. Each observation constrains a group of possibilities rather than revealing the geometry itself. This is a common feature of neutron star physics. Matter cannot be removed from the star. Its phases must be inferred from behavior. A cooling curve, a glitch, a flare, or a missing gravitational wave signal becomes part of the evidence. At still greater density, the rods and sheets lose their identity. The contrast between nuclear regions and the surrounding neutron fluid fades. The structures merge into nearly uniform matter. The crust ends. Below it lies the outer core, where separate nuclei no longer survive, and most of the star's mass is contained in a fluid made primarily of neutrons, with smaller numbers of protons, electrons, and muons. The solid framework has disappeared, but the matter does not become simple. The neutrons remain paired. The protons may conduct electricity without resistance. Magnetic fields are confined into narrow tubes, while quantum vortices continue through the fluid. The journey has reached a deeper ocean. Below the final pasta structures, the crust gives way to the outer core. Separate nuclei no longer survive. The density is too high, and the distinction between one nucleus and the next disappears into a continuous fluid made mostly of neutrons. This region contains most of the star's volume and a large fraction of its mass. The word fluid is accurate, but incomplete. The outer core is not a hot liquid in the ordinary sense. It is a dense quantum ocean where particles occupy states determined by the Pauli exclusion principle and interact through the strong nuclear force. Neutrons dominate, while protons, electrons, and muons appear in smaller numbers to preserve charge balance and chemical equilibrium. The exact fractions matter. A few percent more protons can change which neutrino reactions are allowed. A change in particle composition can alter cooling, pressure, magnetic behavior, and the rate at which different layers exchange momentum. the neutrons are expected to form a superfluid. As in the inner crust, attractive interactions allow neutrons near the Fermi surface to pair. The structure of those pairs may change with density. In some regions, the pairing is likely similar to the simple singlet state found at lower density. Deeper in the outer core, a more complicated triplet pairing may become favored. These labels describe how the spins and orbital motion of the paired neutrons combine. The details are difficult to calculate because the interactions occur in matter far denser than any stable laboratory sample. The broad consequence is clearer. Once the neutrons pair, the fluid can move without ordinary viscosity and carry rotation through quantized vortices. The vortex array that begins in the crust may continue through the core, linking distant layers of the star. The protons behave differently because they carry electric charge. They are also fermions and may form Cooper pairs. When charged particles pair and condense into a common quantum state, the result is superconductivity. Electrical current can persist without the resistance found in ordinary conductors. The outer core may therefore contain neutron superfluid and proton superconductor in the same volume. This combination changes the magnetic field. In a Type II superconductor, magnetic flux does not pass through the material uniformly. It is divided into narrow, quantized tubes. Each tube carries a fixed amount of magnetic flux and is surrounded by circulating proton currents. A neutron star can contain an immense number of these flux tubes. They thread the core in a dense forest, shaped by the magnetic field inherited from the star's birth and by its later evolution. The average field may be smooth on large scales, while the microscopic structure is divided among countless filaments. The neutron vortices and proton flux tubes occupy the same region. They can cross, pin, drag, or cut through one another. Each possibility transfers momentum differently between the neutron superfluid and the charged component, which is tied more closely to the crust through the magnetic field. This interaction may control how quickly the core responds during a glitch. If vortices are strongly coupled to flux tubes, part of the outer core can remain linked to the crust. If they move more freely, a larger reservoir of angular momentum can stay hidden. The observed rise and recovery of a glitch place limits on these couplings, but no single model explains every pulsar. The same microscopic interaction influences long-term spin-down. As the star slows, vortices must move outward. If they drag flux tubes with them, the magnetic field is forced to migrate through the core. If they cut through the tubes instead, energy is dissipated and the coupling changes. The evolution may take thousands or millions of years. The magnetic field seen at the surface is therefore connected to slow motion deep inside the star. Its decay is not simply the fading of an external magnet. It depends on electrical currents in the crust, superconducting structures in the core, and stress exchanged between them. The superconducting state may not fill the entire core. Its survival depends on temperature, density, and magnetic field strength. In an ordinary pulsar, proton pairing may be widespread. In a magnetar, the internal field could exceed the critical strength for superconductivity in some regions. Where superconductivity is destroyed, magnetic flux is no longer confined into narrow tubes. The field can pass through matter more continuously. This may create boundaries inside the core where superconducting and normal regions meet. Magnetic stress can accumulate there, changing how the field rearranges over time. The strongest fields also alter particle motion directly. Charged particles spiral around magnetic lines. At very high field strength, their allowed transverse motion is quantized into discrete Landau levels. Across much of the outer core, this effect may be modest, but in magnetars, it can influence transport and pressure. Heat also moves differently through this quantum ocean. Neutrons, protons, electrons, and muons each carry energy. Pairing suppresses some scattering processes and reduces heat capacity. It also creates new neutrino emission when pairs form or break. The star cools through a competition among these channels. One important set of reactions is called the modified Urca process. A neutron changes into a proton, electron, and antineutrino. While another nearby nucleon helps conserve momentum, the reverse reaction also occurs. These processes release neutrinos that escape from the star and carry energy away. A faster route, called direct URCA, becomes possible only if the proton fraction is high enough. Then, a neutron can transform directly into a proton, electron, and antineutrino without the extra assisting particle. The reverse reaction follows as well. The cooling rate increases sharply. Whether direct URCA operates depends on the equation of state. Some models allow the required proton fraction only in the most massive stars. Others prevent it entirely. Observed surface temperatures can therefore constrain the particle composition of the core, though age, atmosphere, magnetic field, and superfluid gaps introduce uncertainty. A cold neutron star may have cooled rapidly through direct URCA or another enhanced neutrino process. A warmer one may lack those channels, or superfluid pairing may suppress them. The same outer core that stores angular momentum also controls the thermal history. Its quantum states determine how quickly heat disappears, how strongly the crust is coupled, and how the magnetic field can move. This region is not perfectly uniform. Density rises toward the center. The neutron pairing pattern changes. The proton fraction may increase. Muons appear when electron energies become high enough to create them. At greater depth, additional particles or phases may become energetically favorable. The outer core is therefore a transition, not an endpoint. Its broad composition is reasonably well understood, mostly neutrons, fewer protons, electrons, and muons, with superfluidity and superconductivity likely present. The exact strengths of pairing, the geometry of flux tubes, and the coupling among components remain active questions. Observations continue to probe them indirectly. Glitches measure angular momentum transfer. Cooling curves test neutrino emission and heat capacity. Pulsar timing follows magnetic braking. Magnetar flares reveal stored stress. Gravitational waves from mergers constrain how the entire star responds to deformation. Each signal touches the same hidden ocean from a different direction. Deeper toward the center, the density rises beyond the range where ordinary nuclear models are secure. The particles known from the outer core may remain, or they may give way to new forms of matter. Before entering that uncertainty, another connection becomes useful. A tiny layer of neutrons around a heavy atomic nucleus on Earth may carry information about the same pressure that shapes an entire neutron star. The outer core is hidden beneath kilometers of matter, yet one of its clues can be found inside a piece of lead small enough to hold in a laboratory. The connection crosses an enormous range of scale. A heavy atomic nucleus and a neutron star are separated by almost 20 orders of magnitude in size. But both contain matter with more neutrons than protons, and both are shaped by the pressure created by that imbalance. Lead 208 is especially useful. Its nucleus contains 82 protons and 126 neutrons. The protons and neutrons do not occupy exactly the same volume. In many models, the neutrons extend slightly farther outward, forming a thin layer around the more evenly mixed center. This layer is called the neutron skin. It is not a separate shell with a sharp boundary. The density of neutrons simply falls away more slowly than the density of protons near the edge of the nucleus. The difference between the average neutron radius and the average proton radius is measured in femtometers, where 1 femtometer is 1 quadrillionth of a meter. That distance is tiny, even by atomic standards. Its importance comes from the force pushing the excess neutrons outward. Nuclear matter tends to resist a large imbalance between neutrons and protons. The energy associated with that resistance is called the symmetry energy. How rapidly the symmetry energy changes as density rises helps determine the pressure of neutron-rich matter. Greater pressure near ordinary nuclear density tends to push neutrons farther toward the edge of lead 208. In neutron stars, related pressure helps determine how strongly matter resists gravity in the outer core and how large the star becomes. The same underlying physics leaves a mark on both objects. Measuring the neutron skin is difficult because neutrons carry no electric charge. Ordinary electron scattering maps the distribution of protons very well, since electrons respond to electric charge. It does not reveal the neutron distribution with the same directness. The PREX-2 experiment uses the weak nuclear force instead. A beam of electrons is sent toward a thin lead target. The electrons are prepared with their spins aligned in one direction and then the opposite direction. The weak force treats those two arrangements slightly differently. The difference in scattering is only a few hundred parts per billion, but it carries information about the weak charge of the nucleus, which is dominated by neutrons. The signal is extremely small. After combining 2 rounds of measurements, PREX-2 reported a neutron skin thickness for lead-208 of about 0.28 femtometers, with an uncertainty of roughly 0.07 femtometers. The central value suggests a comparatively thick neutron skin. Within many families of nuclear models, a thicker skin points toward a symmetry energy that rises more rapidly with density. That would imply greater pressure in neutron-rich matter near nuclear saturation density, the density found inside ordinary heavy nuclei. Greater pressure often leads to a larger predicted neutron star radius. The word often is necessary. The relationship is not a direct conversion from one measured length to another. A lead nucleus samples matter near and somewhat below nuclear saturation density. A neutron star extends from a low-density crust to a core several times denser than an atomic nucleus. The behavior of matter at those greater densities cannot be fixed by the lead measurement alone. Correlations depend on the class of models being used. 2 equations of state can reproduce a similar neutron skin, while predicting different behavior deeper inside a star. Phase transitions, 3 particle forces, or changes in particle composition can weaken the apparent link. PREX-2 therefore provides a rung on a density ladder, not the top of it. The lower rungs come from nuclei studied on Earth. Heavy ion collisions, nuclear masses, collective vibrations, and parity-violating electron scattering constrain matter near familiar nuclear density. Higher rungs come from pulsar masses, X-ray radius measurements, merger signals, and tidal deformation. A consistent equation of state must touch them all. The PREX-2 central value initially drew attention because some analyses connected it with relatively large neutron star radii. At the same time, gravitational-wave observations and several astrophysical inferences tended to favor more moderate pressure over part of the same density range. This is not a clean contradiction. The experimental uncertainty remains broad. The translation between neutron skin and stellar radius contains model assumptions. Astrophysical measurements also carry uncertainties involving distance, atmosphere, hotspot geometry, and waveform modeling. When these sources are combined, the allowed region becomes narrower, but not singular. A second experiment adds another layer. The CREX measurement examined calcium-48. Calcium-48 has far fewer nucleons than lead-208 and is more accessible to detailed microscopic calculations. Its measured neutron skin was comparatively thin. Many models had difficulty reproducing both the thicker central value from lead and the thinner result from calcium at the same time. This does not mean either experiment must be wrong. It means the structure of the nuclear force may contain details that broad model families do not yet capture well enough. The tension has encouraged closer study of 3 nucleon forces, surface effects, and the density dependence of symmetry energy. A model that describes one nucleus beautifully may fail for the other. A model that fits both must still support heavy neutron stars and remain consistent with merger data. The small nuclei are demanding the same honesty as the stars. This connection is strongest for the outer portions of the core rather than the deepest center. The neutron skin probes pressure around nuclear saturation density. That pressure influences the crust-core transition, the thickness of the crust, and the radius of lower-mass neutron stars. The innermost core reaches densities too high for the laboratory result to determine on its own. Still, The scale of the connection is unusual. In the laboratory, the relevant difference is a fraction of a femtometer. In the sky, the consequence may appear as a change of kilometers in the radius of a neutron star, filtered through theory and combined with other observations. A minute shift at the edge of one nucleus becomes evidence about the shape of a star. This is possible because the equation of state is not tied to one object. It is a statement about matter. The same symmetry energy that influences where neutrons settle inside, lead also contributes to the pressure of matter dominated by neutrons. The environments are not identical, but the physical language is shared. Future parity violation measurements can reduce the uncertainty in neutron distributions. Improved nuclear calculations can test whether lead and calcium can be explained together. Better X-ray pulse profiles and gravitational wave detections can tighten stellar radii and tidal deformabilities. Each result narrows a different part of the equation of state. No single experiment opens the neutron star. The interior is approached through overlap. A nucleus constrains one density. A pulsar mass rules out matter that is too soft. A radius limits pressure over another range. A merger tests how the whole star yields to an external gravitational field. Together, they form a map without a direct image. The lead nucleus leaves the path at the threshold of greater density. Beyond the region it can constrain, new particles may appear, and neutrons themselves may no longer remain the most useful description of matter. The next layers belong to the uncertain inner core, where the equation of state may change its form entirely. The inner core begins where reliable nuclear models start to separate from one another. Density has risen to several times that found inside an ordinary atomic nucleus. The particles known from the outer core may still be present, but the energy required to keep adding neutrons to the highest occupied states has become large enough that other arrangements can compete. The first possibility involves hyperons. Hyperons are relatives of protons and neutrons. They are built from three quarks, but at least one of those quarks is strange rather than up or down. Under ordinary conditions, hyperons decay almost immediately. Inside a neutron star, chemical equilibrium and immense density may allow them to remain. Their appearance can lower the total energy of the matter. Instead of forcing every new baryon into an increasingly energetic neutron state, the system gains additional particle species. Some of the pressure carried by the neutron sea is redistributed among lambda, sigma, or xi hyperons. This tends to soften the equation of state. A softer equation of state produces less pressure at a given density. Many early hyperonic models therefore predicted maximum masses well below the masses of the heaviest observed pulsars. The contradiction became known as the hyperon puzzle. The puzzle does not prove that hyperons are absent. It shows that their interactions are not understood well enough. Hyperon-nucleon and hyperon-hyperon forces are difficult to measure because stable beams and targets of hyperons do not exist in the same way as ordinary nuclear matter. Laboratory experiments study hypernuclei, nuclei containing one or more hyperons, but the available data remains sparse. At neutron star density, three-particle interactions may also become important. Repulsive forces involving hyperons can restore pressure. Recent many-body calculations explore whether momentum-dependent interactions, three-body forces, or different couplings can allow hyperons to appear without reducing the maximum mass below 2 solar masses. Some models succeed. None has yet established that nature chooses one specific solution. A second possibility begins deeper, where the identity of a neutron may itself become less useful. Every neutron contains three quarks held together by the strong interaction, one up quark and two down quarks. In ordinary nuclei, those quarks remain confined inside individual protons and neutrons. At sufficiently high density, the boundaries between neighboring nucleons may overlap until quarks move through a larger shared region. This is called deconfined quark matter. The transition need not resemble a sudden melting point. Some equations of state contain a sharp first-order phase transition with hadronic matter on one side and quark matter on the other. Others allow a broad crossover, in which quark-like behavior grows gradually, while baryonic correlations remain. The distinction affects the star. A strong transition can create a density jump and reduce the radius of a massive star. A gradual crossover may leave no clear boundary at all. The core could contain matter that is neither a simple gas of neutrons nor a freely moving quark plasma, but an intermediate, strongly coupled phase. The quark matter inside a cold neutron star is not the same as the hot quark-gluon plasma produced in heavy ion collisions. Collider experiments create tiny fireballs with very high temperature and comparatively low baryon density. The neutron star core is cooler in the particle physics sense, highly compressed, and held in beta equilibrium for a long time. Quarks there may pair. The strong interaction gives quarks a property called color charge. Under suitable conditions, attractive channels allow quarks near their Fermi surfaces to form pairs. This produces color superconductivity, a phase that resembles electrical superconductivity only in its broad quantum structure. The paired state can take several forms. In the two-flavor color superconducting phase, some up and down quarks pair, while other quarks remain unpaired. At still greater density, up, down, and strange quarks may participate in the color-flavor-locked phase. In that arrangement, color and flavor are linked through the pattern of pairing. The size of the pairing gap matters. A large gap changes pressure, heat capacity, neutrino emission, and the way oscillations are damped after a merger. Recent work combines neutron star observations with high-density theory to limit which pairing strengths remain possible. The constraints are not yet a detection of color superconductivity. They show that some versions of the phase fit the measured masses and radii better than others. Quark matter does not automatically soften the star beyond survival. Its effect depends on the transition density, the strength of repulsive quark interactions, and the speed of sound in the new phase. A sufficiently stiff quark core can support a star heavier than 2 solar masses. A weakly supported one cannot. This is why the presence of massive pulsars does not by itself rule out quark matter. Some analyses that combine low-density nuclear theory, observed masses, radius estimates, and perturbative calculations at extremely high density find that the cores of the most massive neutron stars may behave in a deconfined way. The conclusion remains model-dependent. The same data can still be described by very stiff hadronic matter under other assumptions. Another group of proposed phases involves boson condensates. At high density, the electron chemical potential rises. It may become favorable for negatively charged kaons to appear and replace some electrons in maintaining charge balance. If many kaons occupy the same quantum state, a kaon condensate forms. Pions may condense under related conditions. These phases can change the proton fraction, reduce pressure, and open rapid neutrino cooling reactions. Like hyperons, they often make the equation of state softer unless additional repulsive interactions compensate. No observation currently identifies a kaon or pion condensate inside a specific star. Cooling data can test the reactions such matter would permit, but surface temperature also depends on age, magnetic field, atmosphere, pairing gaps, and the composition of the crust. A cold star may have an exotic core, or it may contain ordinary particles undergoing a fast process such as direct Urca. Several candidate phases can produce similar external behavior. A smaller radius, rapid cooling, unusual oscillation frequencies, or a modified merger signal may point toward a change in composition. None of these signatures is unique on its own. The same effect can arise from different equations of state. The inner core, therefore, remains a problem of inference. Hyperons may appear before quarks. Quarks may emerge gradually without a sharp boundary. Meson condensates may coexist with baryons. Color superconducting phases may occupy only the centers of the heaviest stars. Some neutron stars may never reach the required density. Mass becomes part of composition. A lighter star may contain only nucleons in its core. A heavier one may cross one or several thresholds. Two objects, both called neutron stars, can therefore contain different forms of matter, even when their surfaces and magnetic fields appear similar. The name describes their origin better than it describes every layer inside them. Observations continue to narrow the possibilities. Heavy pulsars demand sufficient pressure. X-ray pulse profiles constrain radius. Gravitational waves measure tidal response. Merger remnants test matter at higher temperature and density. Nuclear experiments limit interactions involving strange particles. The evidence does not yet select one interior. What remains is a set of allowed paths through dense matter. Some end in hyperonic cores. Some continue into quark phases. Others preserve hadronic matter to the highest densities reached before collapse. A final possibility follows from a strong phase transition. If the change in composition is large enough, the mass-radius relation may split into more than one stable family. Two stars could carry nearly the same mass while hiding cores of entirely different matter. A strong phase transition can change more than the composition of a neutron star. Under the right conditions, it can divide the mass-radius relation into two separate stable paths. The first path contains stars supported mainly by hadronic matter, where protons, neutrons, and perhaps heavier baryons remain the useful degrees of freedom. As central density increases, the star grows heavier and usually becomes more compact. Along an ordinary stable sequence, each mass is associated with one main range of radii. A sufficiently strong first-order transition can interrupt that sequence. At the transition pressure, dense hadronic matter may convert into a new phase, often modeled as deconfined quark matter. The energy density can rise abruptly while pressure changes much less. That jump weakens the star's immediate ability to resist compression. The first hybrid configurations may become unstable. As central density rises further, however, the new phase can become stiff enough to support matter again. Stability returns on a second branch of solutions, separated from the original neutron star branch by an unstable interval. This second branch is sometimes called a third family of compact stars. White dwarfs form one family. Ordinary neutron stars form another. Hybrid stars created after a strong internal transition can form the third. Where the mass ranges overlap, twins appear. One member of a pair can be built mostly from hadronic matter with only a small exotic core, or none at all. The other can contain a large quark matter core. Their gravitational masses may be almost equal, yet their radii can differ by kilometers. The difference would appear in compactness. The smaller twin bends light more strongly. Its surface redshift is larger. Its tidal response during a binary inspiral is weaker because a more compact star is harder for a companion's gravity to deform. The term twin does not mean that the two stars were born together. It describes two equilibrium structures allowed by the same equation of state. Nature could produce one or the other depending on mass, rotation, and the path taken through the phase transition. The transition must satisfy narrow conditions. If the jump in energy density is too small, the mass-radius curve remains connected, and no clearly separated second branch forms. If the jump is too large, the star can become unstable and collapse before the high-density phase provides enough pressure to restore equilibrium. The quark phase must therefore soften the star strongly enough to create a break, then stiffen enough to support observed pulsars near two solar masses. That combination is possible in theoretical models. It is not yet known to occur in nature. The two branches may also occupy only a narrow mass interval. This makes twin stars difficult to form and harder to identify. A precise mass measurement is not enough. The radius of each object must also be known accurately. Current radius measurements still have uncertainties large enough to hide the difference in many cases. A future population could change the situation. If several stars, with nearly the same mass divided into two groups, one with larger radii and one with smaller radii, with few stable objects between them, that pattern would be difficult to explain through a smooth equation of state alone. One unusual star would be less persuasive. Atmospheric assumptions, distance errors, magnetic hotspots, or model choices could shift an individual radius estimate. A repeated split across several objects would carry greater weight. X-ray pulse profile modeling is one route toward that test. Pulse shape depends on compactness, hot region geometry, and the bending of light around the surface. Radio timing supplies precise masses in selected binary systems. Gravitational waves provide a second route. During inspiral, each star develops a tidal bulge in response to its companion. The dimensionless tidal deformability measures how readily that shape changes. It depends strongly on radius. Two equal-mass twins with different radii would therefore possess different tidal deformabilities. A binary containing a compact hybrid twin could produce a weaker tidal imprint than a binary of hadronic stars with similar masses. GW170817 constrained the combined tidal response of its two stars, ruling out many equations of state that made ordinary neutron stars too large and easy to deform. The event remained compatible with several equations of state containing phase transitions. One signal could not identify a second stable branch. Future detections can compare systems across different masses. A phase transition may leave a change in the relation between mass and tidal deformability. Stars below the threshold would follow the hadronic branch. More massive stars could enter the hybrid branch and become unexpectedly compact. The transition may also affect the final moments before merger. A sharp internal density change can alter oscillation frequencies and the way energy moves through the interior. These effects are subtle during inspiral, but more sensitive detectors may begin to resolve them. After contact, the differences become larger. The merger remnant passes through densities and temperatures beyond those of either original star. A transition to quark matter can change how rapidly the central region contracts. The frequencies of post-merger gravitational waves and the time before collapse into a black hole. A sudden softening can drive the remnant toward greater compactness. A stiff high-density phase can delay collapse. The outcome depends on total mass, rotation, thermal pressure, and the location of the transition. Current detectors rarely measure post-merger frequencies with enough sensitivity at typical event distances. The next generation of observatories is intended to reach farther into that part of the signal. Even the birth of twins is uncertain. A star formed in a supernova may settle first on the hadronic branch. Continued accretion or spin-down can raise its central density until the transition begins. If a stable hybrid branch exists, the star might contract into the denser configuration rather than collapsing directly into a black hole. The conversion could release energy through neutrinos, heat, or changes in rotation. Its observable signature depends on how quickly the new phase spreads and how much of the star transforms. Recent models suggest that the allowed mass window can be narrow enough that only particular supernova, remnants, accreting systems, or merger products reach the second branch without passing into instability. The absence of known twins is therefore not yet evidence against them. The idea remains useful because it turns a microscopic phase transition into a macroscopic pattern. Quarks cannot be seen inside the core. A split in the mass-radius relation could reveal their presence through kilometers rather than through individual particles. That would be the final reversal in the journey inward. The object called a neutron star may not always be supported by neutron-rich hadronic matter all the way to its center. Two stars carrying the same mass may hide different interiors, different radii, and different responses to gravity. No confirmed pair has yet established a third family of compact stars. The observations are still too sparse, and the equations of state remain broad enough to allow several interpretations. The possibility stays open. Mass measurements mark the vertical scale. X-rays measure compactness. Gravitational waves test deformability. Cooling follows the available particles. Each signal approaches the same hidden transition from a different side. Beyond that point, the interior cannot be followed any farther with present evidence. The path through the star has reached the place where measured structure gives way to allowed possibilities, and where the deepest matter remains quiet beneath the surface. The deepest matter in a neutron star cannot be seen directly, yet it leaves traces in nearly every signal that escapes. The star does not reveal one complete answer. It offers several incomplete ones, each shaped by a different part of the interior. Radio pulses provide the most precise clock. Their arrival times record the slow loss of rotational energy, sudden glitches, orbital motion, and subtle changes in the magnetosphere. A long sequence of pulses can expose a variation smaller than one rotation in many millions. That precision turns motion at the surface into evidence about superfluid vortices far below it. X-rays carry a different message. Thermal radiation rises from the surface after heat has traveled through the crust. Its spectrum depends on atmospheric composition, magnetic field, and gravitational redshift. Its pulse shape depends on hotspot geometry and the bending of light around the star. When these effects are modeled together, the result can constrain mass and radius. Neither measurement is simple. A hydrogen atmosphere does not produce the same spectrum as a carbon atmosphere. A circular hotspot does not pulse like a crescent-shaped one. Magnetic fields change how heat reaches the surface. Distance and interstellar gas alter the light before it reaches a telescope. Each uncertainty must be carried through the calculation rather than hidden. Cooling adds a slower record. A young neutron star loses most of its internal energy through neutrinos. The rate depends on which particles are present and which reactions are allowed. Superfluid pairing can suppress some reactions while opening others during the formation and breaking of pairs. A star that remains warm for thousands of years may contain different cooling channels from one that fades quickly. The surface temperature is only the final layer of that history. Accreting neutron stars offer a more controlled experiment. Matter falling from a companion compresses the crust and releases heat through a sequence of nuclear reactions. When accretion stops, the crust cools toward the core temperature. Telescopes follow the decline over months or years. The shape of that cooling curve reveals how well the crust conducts heat, how much energy was deposited, and how strongly the crust is coupled to the core. A highly conductive lattice cools differently from a disordered one. A superfluid inner crust has a different heat capacity from normal matter. A pasta layer can delay heat flowing outward. The star performs the experiment while the sky remains quiet. Gravitational waves test the whole object at once. During a binary inspiral, the companion's gravity deforms each neutron star. The size of that deformation depends strongly on radius and on the stiffness of the equation of state. A compact star changes shape less. A larger star develops a stronger tidal bulge. The waveform carries that response in the final orbits before contact. After merger, the remnant explores densities and temperatures that isolated stars cannot reach. Its oscillation frequencies depend on radius, rotation, thermal pressure, and the possible appearance of new phases. If a strong transition occurs, the central region may contract, shifting the gravitational wave spectrum and changing the time before collapse. Most current detections cannot resolve that post-merger signal well. The frequencies are high, the events are distant, and the radiation fades quickly. Future observatories are designed to listen more clearly. Continuous gravitational waves provide another possibility. A rotating neutron star with a persistent asymmetry changes the surrounding gravitational field in a repeating way. A small mountain, an internal magnetic distortion, or an unstable oscillation can produce a narrow signal lasting for years. No isolated neutron star has yet yielded a confirmed continuous detection, but the upper limits already restrict how distorted some pulsars can be. Non-detection is not empty. It tells how large a mountain cannot be, how much energy cannot be leaving through certain modes, and which combinations of crust, strength, and magnetic field are unlikely. Laboratory physics fills the gaps between astronomical signals. Measurements of neutron-rich nuclei constrain the symmetry energy near nuclear density. Heavy ion collisions test how nuclear matter responds to compression. Hypernuclei provide limited information about interactions involving strange particles. Particle colliders create quark-gluon plasma at high temperature, offering a different view of the strong force. None reproduces the cold, dense center of a neutron star. The laboratory reaches one region of the phase diagram. The star occupies another. Theory builds the bridge, and observation tests whether the bridge can carry all the available evidence at once. This is why no single measurement settles the interior. A radius estimate can favor a range of pressure. A heavy pulsar can reject equations of state that are too soft. A cooling curve can test neutrino reactions. A glitch can measure an angular momentum reservoir. A merger can constrain tidal deformability and the lifetime of a remnant. The strongest conclusions appear where these paths overlap. An equation of state that supports heavy pulsars but predicts radii far larger than X-ray and gravitational wave measurements becomes difficult to maintain. A model that matches radii but collapses below the mass of a known pulsar fails for a different reason. A proposed exotic phase must fit both the microscopic theory and the macroscopic stars. The interior is narrowed through consistency. The process is slow because each improvement exposes another uncertainty. Better pulse profiles require better atmosphere models. More precise merger signals require better descriptions of matter at finite temperature. Stronger nuclear constraints require more reliable many-body calculations. The unknown center does not retreat in one dramatic step. It becomes smaller by degrees. A future observation may reveal a radius split between equal-mass stars. Another may identify a post-merger frequency inconsistent with purely hadronic matter. A very massive pulsar may push the lower bound on stiffness higher. A nearby continuous wave source may measure the strength of the crust directly. Any one of these would change the map. Until then, the neutron star remains an object known from its edges. Radiation leaves the surface. Pulses record the rotation. Gravitational waves carry the motion of the whole star. Nuclear experiments reproduce fragments of the same forces on Earth. The center itself remains silent. That silence is not a lack of science. It is the boundary that gives every measurement its meaning. The star contains matter, pressed beyond direct experiment, yet it still allows questions to be asked with precision. A city-sized sphere becomes a meeting place for gravity, quantum mechanics, nuclear forces, and observation. Each signal crosses a different layer. Together they approach the core without entering it, and leave the final structure open. The journey can now begin to move outward again. The deepest core remains where it has always been, beneath layers of quantum matter, silent and unreachable. Around it, the outer core continues its slow rotation. Vortices hold their places. Magnetic flux threads the fluid. Above them, the nuclear pasta keeps its strange folded shapes, and the crystal crust carries the weight of the entire star without a sound. Farther out, the atmosphere releases a faint stream of X-rays into space. Those photons climb through curved space-time, losing a little of their energy as they leave. They cross the expanding darkness and travel for years before reaching a distant telescope. The neutron star grows smaller behind them. Its pulses continue at a measured rhythm. The surrounding supernova remnant thins into the interstellar medium. Heavy elements drift into colder clouds, waiting for future stars and worlds that have not yet begun to form. Nothing here needs to hurry. The body can settle more deeply into stillness, while the distant star continues turning. The shoulders can soften. The muscles around the eyes can release. The breath can become quieter without being guided or counted. Beyond the room, beyond the night sky, the compact remnant remains suspended in darkness. Its surface is hot, its interior dense, yet from so far away it is only a small point of light, appearing and fading with every rotation. The unanswered questions can remain unanswered for now. The core does not need to be open tonight. The equations can rest. The signals can continue their long passage across space, while thought grows softer and less distinct. Only the slow rhythm remains. Then the darkness around it, And then the quiet beyond that is greater than is greater than is greater than. End of script. Sleep well.